Okay, in this video we're going to talk about linear growth and the recursive and explicit equations, how we use them, and solve some problems with them. So this problem I already had up from the last video. So you have $10,000 in a bank account and spend $200 each week. So what I want to talk about is what the recursive equation and the explicit equation look like for this particular situation. Okay? And so I want to start off by just talking about a variable, just kind of a definition. So this is a little bit different than the variables that you've seen before because it's going to have a subscript, but I don't want that to confuse you. So we're going to take and create two variables. So n is going to be our time variable. So this is going to be the number of weeks. So we're going to start at week 0. Then we're going to have week 1, week 2, week 3, and so on and so forth. And so n is going to represent that. Okay? So like week 0, week 1, week 2 is the time. The other variable that we're going to have is going to be a sub n. So this is a with a subscript n. And so this number is going to change. Okay? So a sub n is going to represent the account balance in week n. Okay? So this is a variable with a subscript. You may or may not have seen variables like this before, but what this does is it gives us a different variable for each different value, right? So we've got a value in week 0, a value in week 1, a value in week 2, week 3, and so on and so forth. So like a sub 0 would be the value in week 0 when we start off. So 10,000. This is also called the initial value. Okay, so we'll throw that around a lot. So the initial value is 10,000. That's a sub 0. After a week, a sub 1, so the value of the account in week 1 would be 10,000 minus 200, 9,800. Okay, a sub 2 would be 9,600 after we've subtracted another $200 from the amount. Okay? So that's just to understand kind of what the variables are. From this, we're going to write down two different equations. Okay? So one of them is going to represent that situation we talked about in the last video, the recursive equation, which represents the situation of we know we start at 10,000 and then we subtract 200 each week. Okay? So the first one we're going to talk about is the recursive equation. So what the recursive equation says is it's trying to write down, we know where we're starting. So we're going to have a sub 0 is equal to our initial value. Okay? So we would write down in this case, a sub 0 equals 10,000. That's our initial value. All we're doing is writing that down. And then the other thing we know in this situation is that each week, to go from the value 1 week to the value in the next week, we subtract 200. Okay? And so if you think about our variables, and this is where it gets a little bit tricky, so pay attention to kind of what I'm saying here. So if you think about getting the value for this week, say we're in week n. We don't want to write down a particular number because we want something that applies to every single week. If we want the value in week n, what we're going to do is we're going to take the value from the previous week. So if we're in week 5, we would take the value from week 4. If we're in week 10, we would take the value in week 9. If we're in week 15, we would take the value in week 14. And so the way we write that mathematically, if we're in week n, we're going to take the value from week n minus 1. Okay? So if n here were 10, n minus 1 would be 9. If n were 15, n minus 1 would be 14. And then we're going to add whatever our absolute change is to that. Okay? Add or subtract, right? It might be adding a negative number, subtracting something. So like in this situation, we would have a sub n is equal to a sub n minus 1. So the current value is equal to the previous value minus 200. We call this the recursive equation, okay? And so what you're going to do to write down a recursive equation for anything, it's always going to be in the form a sub 0 equals whatever your initial value is, a sub n is equal to a sub n minus 1 plus or minus whatever your absolute change is from one step to the next, okay? And this is just a picture of how we can get the value for the next one from starting at the beginning and then adding or subtracting on the same amount each time, okay? So this is called the recursive equation. That's how you write it down. The other equation that we're going to look at, which you're probably more familiar with, is what's called the explicit equation, okay? And so in the explicit equation, is going to go directly to the value for a sub n, okay? So it's not going to say, oh, okay, we know the beginning, then we can get a sub 1, then a sub 2, then a sub 3, and so on and so forth until we get to whatever n we want. The explicit equation dives right in and says the value of the account after n weeks, a sub n, is going to be the initial value plus that absolute change each time. So whatever our absolute change is each time times n, okay? And so in this particular example, a sub n would be equal to 10,000 minus, right, because our absolute change is negative, 200 times n. And this is probably the form that you've seen before, right? So if we want to know the value on day 2, a sub 2, we would get 10,000 minus 200 times 2, which is 9,600. Exactly what we found earlier with the recursive equation. Okay? So in a lot of ways, the explicit equation is more useful because it lets you get any value kind of immediately. And we'll talk about another way in which it's more useful in a moment, which is to go the other direction, to figure out when you'll hit a particular value. Okay? So using either of these equations, you can solve a lot of problems, right? So if you wanted to know what the value of the account was going to be after 10 weeks, you could use the recursive equation. You could start at 10,000, subtract 200, subtract 200, subtract 200 10 times. Or you can use the explicit equation, and you could say after 10 weeks, I'll have a sub 10 equals 10,000 minus 200 times 10, which would give you $8,000 left in the account. Either one you can use to solve these equations, okay? So the important thing to recognize is how you build the equation first from a problem. You read a problem, get both equations, and then use whichever one you want to solve the problem, okay? So let's look at another problem and answer a few questions. Okay, let's look at a problem where we can solve for linear growth and see, set up the equation, and then we'll solve some problems. So this is a baseball player's number of home runs is increasing linearly. Let's see, in 2013, they hit 35. In 2016, they hit 50. How many will they hit in 2017, 2020, And then we'll add another question on in a second. It's a little bit harder. Okay? So the first thing to notice here is that while the initial value is possible to find, for one thing, we need to be a little bit careful with our units. So if we're going to say that the number of home runs, and let's use h as our variable, h sub 0 equals 35, right? That's our initial value. Then we need to make sure that we remember that the number of years, n, is the number of years since 2013, right? So be very careful. N is years since 2013, right? Because if you wanted to know the number of home runs that they hit in 2017 and you plugged in n equals 2017, you get a really huge number, okay? So be careful. You can always use n to be number of years since sometime, but just make sure you remember that you're doing it, okay? So if our number of home runs in year 0 was 35, the other thing that we know here is that in 2016, they hit 50, okay? So the absolute change from one year to the next is not 50 minus 35, right? So remember, if we want to know absolute change, we want the absolute change over each year, okay? So 2016, that's n equals 3, okay? Right? Because it's 3 years from 2013. So we know h0 equals 35. We know h3 equals 50, okay? And so if we want to figure out what the absolute change is each year, well, we need to take 50 minus 35 and divide by 3, right? And find that average change over those 3 years. So the absolute change each year is going to be 50 minus 35 divided by 3 minus 0. Okay, and so for those of you who've seen maybe some other things, this is also called the slope. Same number, represents the same thing. And so in this case, we get 15 divided by 3 is 5. Okay? So what we know is that we're starting at 35, we're going up by 5 each year. Okay? And so that's enough to figure out our two equations. So we can figure out both our recursive equation, which would be h0 equals 35, h sub n equals h sub n minus 1 plus 5, because we're adding on 5 each year, so the previous value, add 5 to get the next value. And then our explicit equation takes the same numbers, right, and writes down directly h sub n, so the number of home runs n years after 2013 is 35 plus 5n. Okay? So those are our two equations. We can use either of them to figure out the answers to our questions here. So if we want to know the number of home runs that they would hit in 2017, we could start at 35, add 5 to get 2014, add 5 to get 2015, and so on and so forth. We could keep doing that. Or, and this is always a little bit easier, so the explicit equation works a little bit better in most situations. So we know 2017 is 4 years after 2013, so that would be h sub 4. So 2017 would be h sub 4 equals 35 plus 5 times 4, which is 55. 2020, well, that's 7 years after 2013, so h sub 7 would be 35 plus 5 times 7. So we would expect them to hit 70 home runs in 2020 if this is growing linearly. Now we'll talk about why 70 home runs is a lot. And so we'll talk about that in a second. This is a danger of kind of assuming that linear growth keeps going. So this is a good example of kind of how dangerous it can be used to just assume that these equations are always right. Because if you think about it, in 2020, they're hitting 70 home runs. Say we look at 2033. Okay, so 20 years after they started playing in 2013, 2033 would be h sub 20. And if this were true, we would expect them to hit 35 plus 5 times 20, 135 home runs that year. Okay? Now, again, I don't know a lot about baseball, but 135 home runs is insane. That's a lot. And this player's been playing for 20 years. Would you expect them to keep getting better and better every single year? Probably not, right? Maybe they get better for a while, but eventually their body starts to catch up with them, they get older, and the number of home runs they hit would just decrease naturally. Okay? So this is the danger of what's called extrapolating from data. So what extrapolation is where we assume that this growth pattern is going to continue on forever. Okay? And that can be a real issue, because if you just assume that it keeps going forever, eventually your data is going to be wrong. Very few things will keep the same pattern of growth always. Okay? So that's one challenge here. So let's talk about one other type of question that we can run into with these. And this is one where the explicit equation is more useful. So I'm going to leave that up. And I'm just going to change my question here. Let me write it in a different color. So let's say, when will they hit say 63 home runs? Okay, so this is another type of question. It's one where the explicit equation is definitely more useful because it can get you a particular value. What we're asking is, for what n is h sub n going to be equal to 63, right? H sub n is the number of home runs, and we're asking when, so we're asking what time, okay? And so what we're going to do to solve something like this is we're going to say 63 is our h sub n, so 63 is equal to 35 plus 5 times n, and we're going to solve for n, right, and find the time. So we do that. That's pretty easy to do here. Subtract 35 from 63, so that's 28. Yeah, 28 equals 5 times n. We divide by 5, so that's going to give us 5.6 equals n. And so what that tells us is that after 5.6 seasons, so somewhere in between 2018 and 2019 would be when they were on pace to hit that many home runs. Okay? So this answer may not necessarily make sense in all situations. So you couldn't say necessarily that 5.6 seasons, but in some situations it will. It's going to depend on exactly the problem that you're looking at. But you should always plug in the value that you're trying to hit in for h sub n, and then solve for n to find the time at which it will happen.